Okay, so the last section is about curve tracing. Okay, so why do we need to study curve tracing? This one is very important in calculus in order to determine, okay, the behavior of the curve or the function. Okay, so even if you have a technology, say for instance GeoGebra, to help you graph the function, so it is very important still to know how to see the behavior of the graph, okay, manually. Okay, so to fully understand how functions and equations are drawn, we have to investigate several factors. Okay, and then it is not always the case that you have a tool, okay, with you in order to graph this function. So let's try to draw this or sketch the curve of a particular function manually. Okay, so in our last unit. Okay, so for the forms of equations, uh, you will be expected to graph, okay, these equations, okay, in rectangular as well as in polar coordinates like this one here. Okay, so what are the factors that we need to consider in graphing, okay, functions? So first we have the behavior, okay, in extreme values. Okay, so if your function, okay, increases or decreases whenever you set very small value of x or very large value of x. Okay, so the next one, you're going to identify the vertical and then we have the horizontal asymptotes. But this one is only for rational functions only. Okay, and then we also have to check the existence of symmetries. Okay, if there's any, and then you're going to identify the intercepts, and then of course you're going to use additional points, okay, in order to check, okay, the behavior of the curve. Okay, now let's have to consider the behavior in extreme values. Okay, so in your function y is equal to f of x, or we have y squared is equal to f of x. Okay, so we need to set a large value of x or small value of x. Okay, so graphing functions, okay, often either increases or we have decreases. When you say increases, your function or the curve goes up, okay, or decreases whenever the graph goes down. Okay, if we have indefinitely or for larger values of x. Okay, and this one happens also when you set, okay, very small values of x, like what, negative values. Okay, so say for instance you set x to be equal to positive 100, or you have x which is equal to negative 100. Okay, so you're going to identify here if the function value is positive or we have a negative value. Okay, so what is the meaning if we have a positive value for this particular function whenever you set a large positive value for x? Okay, so then the graph increases indefinitely to the right. Okay, and if the resulting value is negative, okay, then the graph decreases indefinitely to the right whenever you set, okay, large positive value for x. Whereas if you consider a large negative value for x, meaning a very small number here, okay, if the resulting value is positive, then the graph increases indefinitely to the left. Okay, whereas if the value is negative, then the graph decreases indefinitely to the left. That is when you set, okay, a very small value for x. Okay. Now, how about testing for symmetry? Okay, so you're given again the function y is equal to f of x, say for instance. Okay, so in order to check if the graph is symmetric with respect to the x-axis like this, okay, you're going to replace y, okay, with negative y. So remember, you have the given function, okay, we have, let's say, y is equal to f of x. Okay, so instead of using y here, you're going to replace y with negative y. Okay, and if the resulting equation is still the same, okay, as the given equation, okay, that would mean that your graph is symmetric with respect to the x-axis. So one example of a graph that is symmetric with respect to the x-axis is this one. Okay, how about if you're going to check if the graph is symmetric with respect to the y-axis? Okay, so this time you're going to replace x, okay, with negative x. So if the resulting equation is the same as the original given equation, okay, nothing has changed after changing x with negative x, then we can say that the graph is symmetric with respect to the y-axis. So where is an example here is this one. Okay, so if we have a graph that is symmetric with respect to the y-axis, as you can see here, this one, the y-axis here divides, okay, the curve into two, okay, equal figures. Okay, and then if we're going to check if the graph is symmetric with respect to the origin, okay, so we're going to replace x and y with negative x and then negative y respectively. And if there's nothing, okay, has changed in the given equation, then we can say that the graph is symmetric with respect to the origin. And one particular example is this. So this is the origin. Okay, as you can see, it divides the curve, okay, into two equal parts. Okay. Next, how about identifying the domain when you're given y squared is equal to f of x? Okay, so when you say domain, these are what? Permissible values of x, okay, that can be substituted in our equation. Okay, so how do we find the domain? You're going to find, okay, the zeros of this function, okay, by equating this to 0. Okay, so now after equating this to 0 and then solving for the zeros of this particular function, you're going to construct, okay, the interval of values, okay, wherein the 0 of f of x serve as the boundaries of the intervals. Okay, and then you're going to choose a test point. You're going to choose a test point. So a test point is actually a number within the constructed interval. Okay, and then what's the next one? You're going to evaluate the function using the test point that you have chosen. Okay, and then you check now the sign, okay, of the resulting function value. Okay, now if the function value is negative, okay, then that would not be included in the domain, okay, of this particular function. Okay, so let's try to find the domain of the given function. We have here y squared is equal to x squared minus 4. So let's make this y squared is equal to x squared minus 4. As you can see here, we need to avoid, okay, the right side to become negative, okay, because you have here y squared is equal to x squared minus 4. This is the same as writing y is equal to plus and minus. We have square root of x squared minus 4. right? Okay, so meaning that your radicand here, okay, must be positive in order to give you a real number. Okay, so in this case, we're going to get, okay, the zeros of this function. Okay, so we have x squared minus 4. Okay, this one can be written as x plus 2. We have x minus 2 and then equate this to 0. So I have x plus 2. We have x minus 2 and then equate to 0. Okay, so this one will give you two values of x. We have x plus 2, which is equal to 0, and then I have x minus 2 is equal to 0. So I have here x is equal to negative 2, and then we have x is equal to positive 2. Okay, so this will serve as the boundaries of our interval. Okay, so now let's construct the interval. First, you consider the number line. So this one is 0, this one is negative 2, and then we have positive 2. Okay, negative 2 and beyond, that will give you negative infinity, okay, to negative 2. Okay, so we're going to exclude negative 2 and then 2 because as you can see, once that you plug in x is equal to 2 and then x is equal to negative 2, the whole thing here will become 0. Okay, but you just need a negative value, okay, in order to exclude that in our domain. Okay, so now we have the first interval, negative infinity to negative 2. Okay, how about the second interval? Okay, so as you can see, you have here negative 2, okay, until we have 2 here. Okay, so but again, you're going to exclude negative 2 and then 2. So you have here your open interval. Okay, how about the third one? We have here 2 and then beyond. Okay, so you have here 2 to positive infinity. So that would now be the third interval. Okay, so we're done with this. Now you're going to choose a test point. Okay, again, your test point must be a number, okay, that is actually between the interval. Okay, so if you have, let's say, negative 3, this is between the given interval, so this one is accepted. Or you may have negative 10. Okay, but in this particular example, let's use the test point, which is negative 3 for the first interval. How about for the next interval? So that is between negative 2 to 2. So let's try to use 0. Okay, and then for the third interval, you have 2 to positive infinity. Let's choose 3. Okay, now if I have, let's say, negative 3, x is equal to negative 3, let's try to find the value of um, our function here. Okay, so you have x squared minus 4. Okay, so in this case, this one will give you uh, positive 5. Okay, so I have here positive 5, and then the other one here, if I will let this to be equal to 0, so you have 0 minus 4, this one will give us negative 4. So meaning that the sign here is negative. Okay, and then if I have, let's say, positive 3 here, okay, for the next value of x, this one will give us again positive 5. Okay, so again, we are avoiding a negative number. Okay, so we have a negative number here. So meaning that we're going to exclude now, okay, the interval negative 2, okay, between negative 2 to 2. Okay, so meaning that I'm going to include negative 2 and 2 because when you substitute here, this one is 0, is still a real number. Okay, so now the domain of our relation would now be half open interval. So you have negative infinity to negative 2. So meaning that 2 is included here. Union, again, your half open interval. Okay, so 2 is included, okay, until we have infinity. Okay, so this would now be the domain of this particular function. Okay, how about your asymptotes? Let's recall that we can just have an asymptote if we have a rational function. Okay, so let's recall that if we have a rational expression P over Q, okay, so this one is undefined whenever your Q is equal to 0. Okay, and that is also similar, okay, to your rational function. So if you have f of x over we have g of x, your denominator g of x must not be equal to 0 to make this function defined. Okay, so the effects of this is the presence of asymptotes in the graph of the function. Okay, so asymptotes come as either vertical, horizontal, or we have here your slant asymptote. But we will just be discussing the vertical and then the horizontal asymptote here. Okay, so for your vertical asymptote, okay, this one is of the form x is equal to a. So the values of a are the zeros of your g of x. Your g of x, remember, would now be your denominator in our rational function. So you have f of x over we have g of x. Okay, so you get the zeros of this. Okay, so that would now be the value of a. Okay, hence to determine the vertical asymptote, you're going to set the denominator to 0 and then we have to solve for x. Okay, so let's try to consider this particular rational function. Okay, so this one is f of x over we have g of x. Okay, so your denominator here is x squared minus 9 and hence you're going to uh, consider this, okay, and get the zeros of this one, okay? So how? By equating g of x to 0, okay? So that means I have g of x is equal to 0, and then you have x squared minus 9 is equal to 0, and getting the factors of this, I have x plus 3, and then the other factor is x minus 3. Equating each factor to 0, that will give you x is equal to -3 and then you have x is equal to 3 here. Okay, so thus our vertical asymptotes are at we have x is equal to -3 and then we have x is equal to +3. Okay, but this one is not the graph of this particular example. Okay, I just illustrated here, okay, a vertical asymptote. Example of a vertical asymptote. Okay. Next, how about your horizontal asymptote? So if we have horizontal asymptote, so again, this one exists only for graphs of the function f of x over g of x when the degree of the numerator is less than, okay, or equal to the degree of your denominator. Okay, so as a summary here, if the degree of the numerator is equal to the degree of our denominator, then you have the line y is equal to b, which is your horizontal asymptote. Okay, wherein b here is the ratio between the leading coefficient of the numerator and then the leading coefficient of the denominator. When you say leading coefficient, this one is the coefficient of the variable containing the highest power. Okay, so if the degree of the numerator is less than the degree of the denominator, then we have your y is equal to 0 as your horizontal asymptote. Okay, so here is an example of your horizontal asymptote, the broken line here. Okay, so let's try to consider this particular example. Okay, so we have to determine the horizontal asymptote or asymptotes of y is equal to 1 over we have x squared minus 9. Okay, since the degree of the numerator, okay, is less than the degree of the denominator, okay, actually here we have the degree is actually 0, not 1. Okay, is less than the degree of the denominator, which is actually 2, then, okay, we have y is equal to 0, okay, must be our horizontal asymptote following this particular rule, okay, because the degree of the numerator is less than the degree of our denominator, okay. So you have y is equal to 0, which is our horizontal asymptote. Okay, how about the next one? We're going to determine the horizontal asymptote or asymptotes of y is equal to 2x squared. All over, we have x squared minus 4. Okay, so you check the degree again of the numerator and then the denominator. Since the degree of the numerator is equal to the degree of the denominator, which is actually equal to 2, okay, then we have the line which is equal, the line y is equal to b must be our horizontal asymptote. Okay, but how do we solve for b? Okay, this one is actually the ratio between the leading coefficients of the numerator and then the denominator. So for the numerator, the leading coefficient here is 2. Okay, because this one is the coefficient of the variable with the highest powers. I have here 2. And then the leading coefficient of um, the variable in our denominator must be 1. Okay, because this is the coefficient of the variable containing the highest power, which is 2. Okay, so you have 2 over 1. And your b here is equal to 2. Thus, the horizontal asymptote, okay, is at y is equal to 2. Okay, so how about tracing the function f of x? So we mean we need to check the behavior of this particular function. Okay, so if you have equations of the form y is equal to f of x, this can be traced by looking the following. Okay, we have the behavior in extreme values, and then we have existence of symmetries, and then we have identifying the intercepts, and then of course we're going to plot additional points. Okay, so let's have here an example. You are asked to trace the graph of y is equal to x squared minus 2x minus 15. Okay, so for the first part, we're going to see the behavior in extreme values. So meaning that you're going to assign a very large value, okay, for x, and then a very small value for x. Okay, so if x is set to be equal to 100, then your y here is equal to 9786. So you're going to substitute the value of x here. Okay, thus that means we have here a positive, okay, large values of x, okay, and then y becomes larger indefinitely, and then that means that the graph goes up indefinitely towards the right. Okay, so if you have 100 here, okay, and then this one is positive, that means that your function will go up, okay, towards the right. Okay, and then what if your x is equal to negative 100? Your y here is positive, okay, 10,185. So that means that for large negative values of x, your y becomes larger indefinitely, and then the graph goes up indefinitely towards the left. So if this one is your negative 100, your graph is like that. Okay, so the behavior is like this. That means it will go up towards the left. Okay, so that is assigning extreme values, okay, for this x to find the behavior of the curve. Okay, next, how about testing for symmetry? Okay, so we have test for symmetry with respect to the x-axis. So what is our technique again? You're going to replace y, okay, with negative y. Okay, so now, since you're given y is equal to x squared minus 2y minus 15, you're going to replace this y by with negative y. So you have negative y is equal to x squared minus 2x minus 15, okay? And then dividing both sides by negative 1, we have positive y is equal to negative x squared plus 2x plus 15, okay? So you compare now the original function with this computed, okay, function, okay? Are they the same? The answer is no. So meaning that this one, okay, is not symmetric with respect to the x-axis because we changed the original function. Okay. How about checking for symmetry with respect to your y-axis? Okay, so this time we're going to replace x with negative x. Okay, so again you have y is equal to, we have here x squared minus 2x minus 15. So that's the original function, okay, that is actually given, okay. Replacing x with negative x, okay, this one result to y is equal to x squared plus 2x minus 15, okay. As you can see, this one differs, okay, in sign. Okay, if you're going to compare the original with the computed or with the new function. Okay, so meaning that this one is again not symmetric with respect to the y-axis. Okay, so how about testing for symmetry with respect to the origin? Okay, so this time you're going to replace x and y with negative x and then negative y respectively. Okay, in doing that, if you have y is equal to x squared minus, we have 2x minus 15, your y here will be replaced by negative y, and then all the x's here will be replaced by negative x. Okay, so simplifying this, what will happen? I have negative y is equal to positive x squared plus 2x minus, we have 15. And then, of course, we're going to divide both sides by negative 1. So I have y is equal to negative x squared, okay, minus 2x plus 15. Notice that we have different signs again, okay? So your obtained function is not the same as the original. And therefore, we can say that this one is again not symmetric with respect to the origin. Okay, so our function is not symmetric with respect to the x-axis, the y-axis, and then we have the origin. Okay. Next, how about the intercepts? Okay, so note that if we are given again y is equal to x squared minus 2x minus 15, you have y squared is equal to x squared minus 2x minus 15, okay? This one is actually, sorry, y only. Okay, y is equal to x squared minus 2x minus 15. This one is actually factorable, the right side. Okay, so if you're going to factor this, I have x and then x for x squared, and then for negative 15, let's try the factors negative 5 and then we have positive 3. Okay, so you check the middle term if you will get negative 2x. So I have negative 5x, so that's negative 5x here. Plus I have, we have 3x. Adding this together will give you negative 2x, which is our middle term. Okay, and then to solve for your x-intercepts, you set y to be equal to 0. Okay, so since I have two factors here, x minus 5x plus 3, you're going to equate this to 0. Okay, so now each factor will be equated to 0. So I have x minus 5 is equal to 0, and then the other one here, x plus 3 is equal to 0. And then solving for the value of x, I have x is equal to 5, and then the other one, x is equal to negative 3. And therefore, for our x-intercepts, this one, okay, has what? Coordinates 5, comma 0, and then the other one is negative 3, 0. Okay, take note of these 2 points because we're going to plot this later. Okay, how about the next? If you're asked to solve for the y-intercept, you're going to set x to be equal to 0. Okay, and then you solve for y. So in this case, if you're going to set x to be equal to 0, so this one is 0, this one is also 0, you only have y, okay, is equal to 15, okay, negative 15. Okay, so in this case, I have y-intercept is at 0, and then you have negative 15. Okay. How about your additional points? Aside from the points, you can now set, okay, aside from the points that we obtained, the x and then the y-intercept, you can actually set, okay, values for x in order to obtain, okay, values for y. Okay, so if you have y is equal to, we have x squared minus 2x minus, we have 15. Okay, so if I have y is equal to, okay, x is equal to negative 2, that is negative 2, the quantity squared, minus we have 2 times negative 2, minus we have 15. Solving for this, I have 4 plus 4 minus we have 15. So that will give you negative 7. Okay, and then, it's negative 7. Okay, so in here, if you let x to be equal to negative 1, please check that you will get negative 12. Okay, and then if x is equal to 1, then I have negative 16. If x is equal to 2, then you have negative 15. Okay, and then if x is equal to 4, then you have negative 7. Okay, so we're going to plot these additional points so we can trace our curve. Okay, you're going to plot the points including the intercepts and then trace the curve based on the information about the behavior of the graph in extreme values. Okay, so let's try this one. We have negative 3, 0, and then we have here 5, 0 for our x-intercepts. Okay, and then the other one, remember that your y-intercept, okay, would be at 0, negative 15. Okay, so you have 0, negative 15 here. Okay, so this one is your x-intercept. We have 2 points here for your, this is your y-intercept, and then I have here your x-intercepts. Okay, and then we're going to plot now the additional points that we obtained. Okay, and then trace the curve. Okay, so look at this. We have now a parabola. Okay, how about the next example? We're going to trace the graph of y squared is equal to x cubed minus x. Okay, so first, in this particular example, you're going to determine the domain, okay, of this particular function. Okay, we did not do this in the previous example because you're just given there y is equal to f of x. That's why we omitted this particular step. Okay, so that means in our previous example, the domain of that particular function, okay, is actually all real numbers. Okay, so how about if you have this particular function, you have y squared is equal to x cubed minus we have x. Okay, we discussed this a while back that if you have a function of the form y squared is equal to f of x, okay, so we need to make sure that f of x here is positive, okay, in order to avoid imaginary numbers. Okay, so now let's try to get the domain of this particular equation. So if you're going to get the factors of the right side here, we have x cubed minus x. This one can be written as we have x cubed minus x, factoring out x, you only have x squared minus 1, okay? But x squared minus 1 is still factorable, okay? So this is now equal to, we have x times, we have x minus 1, we have x plus 1. Okay, you have difference of two squares. And then you're going to get the zeros of this f of x. Okay, so meaning that you're going to equate this to 0. Okay, what do we get? I have x is equal to 0, and then the other one, x minus 1 is equal to 0, and then you have x plus 1 is equal to 0. Okay, so in here, this implies that x is equal to positive 1, okay, and then x plus 1 is equal to 0 means that your x here is equal to negative 1. So you have 3, okay, boundaries here. You have negative 1, 0, and then we have 1. Okay, so meaning that when you substitute this in our equation, okay, your y here will give you a 0 value. Okay, so your goal here is to eliminate, okay, all the values that will make your y negative, okay, to avoid imaginary number. Okay, so now if I'm going to draw, okay, a real line here and then locate these values, we have here 0, this is negative 1, and then this one is positive 1. Okay, so from 0, from negative 1 onwards, okay, you have here now an open interval. We have negative infinity, negative 1 here. So that is our first interval, okay? How about the next? We have between negative 1 and then we have 0. Okay, so you have here an open interval, okay, we have negative 1 and comma, we have 0. Okay, so how about the next? We have here between 0 and then we have 1. Okay, so I have here 0 comma 1. Okay, and then how about the next? We have 1 onwards. Okay, so you have here 1 comma infinity. So you have here an open interval again. Okay, we did not consider again negative 1, 0, and then 1. Okay, because these values, when you plug in our equation, will give you 0. Okay, our goal is to determine the values that will make your y negative so we can eliminate them. Okay, so now we constructed the 4, okay, intervals. You have to choose now your test point. Okay, this open interval, negative infinity to negative 1. Okay, so I will choose a number between this, say for instance negative 2. Okay, and then a number between negative 1 and 0, say for instance we have negative 0.5. Okay, and then a number within the interval 0 and then 1, we have 0.5. And then a number, okay, within this interval 1 to positive infinity, let's say we have positive 2. Okay, and then you substitute now the values, okay, of x here from our original from our original equation. Okay, so you have here y squared is equal to, we have here x cubed minus we have x. Okay, so I have, let's say, negative 2 cubed minus we have negative uh, 2. Okay, so what do we get? I have here negative 8 plus we have 2. So you have negative 6. Okay, how about the next one? If you plug in negative 0.5 in our equation here, you will get positive 0.375. Okay, and then if you plug in positive 0.5, you will get negative 0.375. And then when you plug in, okay, 2 in our equation here, you will get positive 6. Okay, so you have to check the signs. Okay, those with negative signs will now be eliminated. Okay, so meaning that you're going to eliminate, okay, the interval, okay, negative infinity, negative 1, okay, and then we also have open interval 0 to 1. Okay, so we're going to eliminate this. Why? Because within this region, okay, it will give you a negative value for your y here. Okay, which in turns will give you imaginary number. Okay, and therefore the domain of our relation, okay, is, we have a closed interval here, negative 1 to 0. Okay, so again we said that if negative 1 is plugged in here and then 0 as well as 0, it will give you a value of 0 for your y, which in this case, y squared is equal to 0. When you extract the square root of this, y is equal to 0, which is actually an element of your real number. That's why these are actually included. Okay, and then also, if you have the interval, okay, from 1 to infinity, okay, it will give you a positive result. Okay, so this one is also included. And of course, I have here a closed, okay, interval because 1 is included. When you plug 1 here, again, it will give you a value of 0 for your y. Okay, so now we know the domain, okay, of our function. Okay, so let's see now the behavior, okay, using extreme values. Okay, so now let's try to observe. If you're going to consider x which is equal to 100, okay, x is equal to 100, you can actually plug in x is equal to 100 because it is accepted, okay, or it is defined, okay, when x, okay, reach a very large number, positive large number because of this interval, okay. So your y will give you plus and minus 999.95, okay. So meaning that for a large, okay, positive value of x, okay, y becomes both infinitely larger and smaller. Okay, thus the graph goes towards two directions simultaneously. When moving to the right, okay, upwards, and then we have downwards. So we have like this. Okay, so when x is equal to 100, note that the equation is only defined, okay, for negative values of x, okay, for negative 1, okay, up to 1 here, okay. So meaning that you cannot set x to be equal to negative 100, okay, because that is not considered in our domain. Okay, so we only have this one. Okay, so how about testing for symmetry? Okay, with respect to the x-axis, okay, again, you're going to replace y, okay, with negative y. So I have the original equation, y squared is equal to x cubed minus x. You're going to replace y with negative y here. Okay, so doing that, we have y squared, okay, is equal to x cubed minus x. So now you compare. As you can see, okay, we have the same result. Okay, so our original equation is the same as the computed one. So meaning that the graph is actually symmetric with respect to the x-axis. Okay, how about if you will test for symmetry with respect to the y-axis? Okay, so this time you're going to replace x, okay, with negative x. So you check the result. So doing that, you have y squared is equal to negative x, the quantity raised to 3, minus we have negative x, okay? So this one will give you y squared is equal to negative x cubed plus we have x, okay? Which is not actually the same as the original equation, okay? So that means this one is not symmetric with respect to the y-axis. Okay, how about testing for symmetry with respect to the origin? Okay, so again, you have y squared is equal to x cubed minus we have x. This one is the original equation. Okay, so now you're going to replace x and y with negative x and negative y respectively in order to determine if the graph is symmetric with respect to the origin. Okay, so we have to substitute negative x, okay, for x here, and then negative y for y. Okay, so what do we get? We have here y squared is equal to, we have negative x cubed plus we have x. Comparing now the signs, okay, this is different from the original equation, and therefore we can say that this is not symmetric with respect to the origin. Okay, how about the intercept? So again, you have to get the factors, okay, of the right side in order to find the x and then the y intercepts. Okay, now to find for the x-intercepts, you're going to set, okay, y or the left side to be equal to 0, and then you're going to solve for x. Okay, we did this one a while ago. So you have x, okay, is equal to 0 for the first factor, and then for the second one, we have x plus 1 is equated to 0. So therefore, that will give you now x, which is equal to negative 1. Okay, and then if you have x minus 1 is equated to 0, you have x is equal to positive 1. And therefore, there are 3, okay, coordinates for your x-intercept. So I have negative 1, 0, okay, because your y here is set to 0. And then you have 0, 0, and then we have 1, comma 0. Okay, how about for your y-intercept? So this time, we're going to set x to be equal to 0. Okay, so if this one is 0, okay, everything else here is 0. Okay, so meaning that your y squared is now equal to 0. Okay, so your y-intercept is located at the origin. So you have your 0, comma 0 as its coordinates. Okay, so remember again the points that we considered. You have 3 x-intercepts and then 1, okay, y-intercept at the origin. And then you consider also the behavior of when we plot the extreme points, okay? And then, of course, we need additional points. Okay, so if you set x to be equal to negative 0.75, you have two values, remember? We have plus and minus 0.57. So what is our equation again? You have y squared is equal to, we have x cubed minus we have x. Okay, when you set the values of x, remember our domain. Okay, because if you set values, okay, for x which is not actually included in our domain, then it will give you, okay, an imaginary number. So be careful. Okay, so y squared is equal to x cubed minus we have x here. When x is equal to negative 0.75, okay, so I have y squared is equal to negative 0.75 cube minus we have negative 0.75. Okay, so y squared is equal to 0.75 raised to 3. Okay, so this one is negative 0.421875 plus we have 0.75. Okay, so in here I have plus 0.75. We're just verifying. Okay, I have negative 0.75 raised to 3. Okay, minus we have negative 0.75. So the answer here is 0.3281. Okay, sorry for this one. 0.3281, or you have here y is equal to plus and minus the square root of 0.3281. Okay, extracting the square root, sorry, this one is correct. We have here y which is equal to plus and minus 0.5728. Okay, so this one is correct. Okay, so you check again these points. Okay, and these are the additional points that we're going to plot. Okay, so look at this one. Take note that we have actually a symmetry. Okay, remember that we check that for this, okay, we have a symmetry, okay, with respect to the x-axis, So meaning that we have this, okay, which is symmetric to my x-axis, and then also this one. Okay, remember the behavior. Okay, when x is equal to 100, okay, you have positive, okay, value of y. Okay, so this one will go up. Okay, and then the other one here will go down. Okay, a negative large value and then positive large value for y. Okay, so this one is the graph of the curve or the equation y squared is equal to x cubed minus we have x. Okay, so this time let's trace the curve of a rational function. Okay, so this equation is of the form y is equal to f of x over we have g of x. Okay, so we're going to consider this time the asymptotes. Okay, so in our previous examples, we did not check the asymptotes because we have there a polynomial. Okay, and then the other one is of the form y squared is equal to f of x. This time, we have here a denominator, so we need to check the asymptotes. Okay, and then we also have existence of symmetries. And then we have to identify, of course, the intercepts, and then we're going to plot additional points. Okay, so given this particular rational expression, okay? So for the vertical asymptotes, we need to consider your denominator x squared plus 3x minus 4, okay? So again, we have to find the zeros of this denominator, okay, by equating this to 0. Okay, so this x squared plus 3x minus 4 is factorable. Okay, so you have factors of x squared, we have x and then x. Factors of negative 4, we have 4 and then negative 1. When you add this, we have 4x, and then the other one here is what? Negative x. Adding this together will give you positive 3x, which is our middle term. And then you equate each factor to 0. So I have x plus 4 is equal to 0, and hence it will give you x is equal to negative 4. And then the other one, equating x minus 1 to 0, you have x is equal to 1. Okay, so in this case, we have here a vertical lines. Okay, we have vertical lines, sorry. We have x is equal to negative 4, and then the other one, x is equal to 1. Okay, so this must be the vertical asymptotes of the graph of this particular rational function. Okay, how about for your horizontal asymptotes? Okay, so you check the degree now of the numerator and then the denominator. Since the numerator, okay, the degree of the numerator is equal to the degree of your denominator, okay, both of degree 2, okay, there must be a horizontal asymptote of the form y is equal to b, like what we discussed a while ago, okay? Wherein, again, b is the ratio, okay, between the leading coefficients of the numerator, and then we have the denominator, okay? So in this case, we have b is equal to your leading coefficient here is 1 for the numerator, and then also the leading coefficient in our denominator is also 1. So we have b is equal to 1 over 1, or your b here is equal to 1. And meaning that the horizontal asymptote would be the line y is equal to 1. Okay, so you take note the vertical asymptotes and then our horizontal asymptote. Okay, how about test for symmetry? So in this case, we have test for symmetry with respect to the x-axis. I will write the original equation. So you have y is equal to x squared over, we have x squared plus 3x minus we have 4. Okay, so again, if we want to check the symmetry, okay, with respect to the x-axis, you're going to replace y with negative y. Okay, so like what we have here. Okay, and then you have to write this in such a way that I have positive y, and then you compare now this resulting equation to the original one. Okay, so as you can see, we have negative here. Okay, we have negative 1 here. Okay, which is different from the original, and therefore, since these two are not equal, we can say that this is not symmetric with respect to the x-axis. Okay, how about if you're going to test for symmetry with respect to the y-axis? Okay, so this time you're going to replace x, okay, with negative x in order to check if the graph, okay, is symmetric with respect to the y-axis. Okay, so doing that, you substitute now negative x, okay, to this variable x, okay, and then simplifying this, you will get x squared on the right side, okay, all over we have x squared minus 3x minus 4, okay, and check the signs again, we have different signs compared to the original, and therefore we can say that this graph, okay, is not actually symmetric. The graph of this function is not actually symmetric with respect to the y-axis. Okay, so how about test for symmetry with respect to the origin? Okay, so again, I will write the original equation. Y is equal to, we have x squared all over, we have x squared plus we have 3x, and then we have here minus 4. Okay, so what is the technique here? You're going to replace x and y with negative x, and then we have negative y. Okay, so now changing this to negative y, we have this one, and then replacing x with negative x, you have this. Okay, and then simplifying this further, this one will give you y is equal to negative of x squared all over, we have x squared minus 3x minus 4. Okay, so in this case, you compare the original from the obtained equation. Okay, so we can say that since these two are not equal, we can say that this is not symmetric with respect to the origin. Okay, how about for the intercept? So again, we have to consider the original equation. So you have y is equal to x squared over, we have x squared plus 3x minus we have 4. Okay, so in this case, to solve for the x-intercept, you set y to be equal to 0, and then you're going to solve for x. Okay, so if that is the case, if I will set this to be equal to 0, okay, you only left with what? X squared is equal to 0, and this one means that x is equal to 0. Okay, and therefore your x-intercept is at the origin. We have the coordinates 0, 0. Okay, how about for the next one? We're going to solve for the y-intercept. Okay, so you have to set x this time to be equal to 0, and then you have to solve for y. Okay, so in this case, I have 0, okay, in our numerator, and in our denominator, this one will give you negative 4. Okay, and hence, if you simplify this, your y is now equal to 0, and therefore the y-intercept is also at the origin 0, 0. Okay, so you take note of this point. Okay, and also the asymptotes, okay, that we obtained. Okay, so how about considering additional points again? Okay, so if you have to consider now, okay, the points here, make sure that your denominator will not be equal to 0. Okay, so our equation here, we have y is equal to x squared over, we have x squared plus 3x minus 4. Okay, this rational function, okay, is defined, okay, for all values of x except, okay, when x is equal to, okay, your uh, x is equal to negative 4 and x is equal to 1. So do not include that in our values of x. Okay, because remember, this function is not defined if our denominator is equal to 0. Okay, when will that happen? Whenever x is equal to 4 and then x is equal to negative 1. Okay, did I mention that correctly? Yes, when x is equal to negative 4 and x is equal to 1. Okay, now you have here x, okay, which is equal to negative 8, negative 6, and so on. And then substitute the values, okay? So you have y is equal to, say for instance, I have negative 8. We have here negative 8, the quantity squared, over we have negative 8 squared plus we have 3 times we have negative 8 minus we have 4. So what is y now? You have 64 divided by, we have 64 minus 24 minus 4. Okay, so this one will give you 1.77 8, or you have here 1.78. Okay, doing the same thing here, you will obtain values of y. Okay, we're going to plot this, okay, including the intercept, and then we're going to trace the curve. Okay, so look at this one. We have your vertical asymptote. We have here x is equal to -4, okay? And then we have x is equal to -1, okay? And then also we have here your horizontal asymptote, okay? With this equation, y is equal to 1, okay? So what will happen to your asymptotes here, okay? The curve, okay, will actually get closer and closer to this asymptotes, okay, but it will not intersect, okay, the asymptotes, okay. So that is actually the behavior of the curve when we have this asymptote, okay. And then you're going to plot now the points, okay. So remember, we have this, okay, as the x and then the y intercepts at the origin, okay. And then these are the points that we obtained, okay. These are the points that we obtained when we have additional points, okay. Now, tracing the curve, okay, so we have this, and this one is your, take note that this one is your vertical asymptote, okay, so the curve will just get closer and closer to this broken line, but it will not actually intersect this broken line, okay. So where else we have this one, okay, you have your vertical asymptotes here. And then also we have another one here. Okay, so that would now be your graph. Okay, and then redrawing this one again will give you this behavior of the curve or graph of that particular rational function. Okay, so we have the next one, polar coordinates. Instead of using rectangular coordinates, this time we can use polar coordinates, okay? So points can also be determined using a different method. So this time, we will be using the polar coordinate. Here, we have here the coordinates r and theta. So what is r? R is the distance between the origin, okay, and then your point P, okay? While theta here is the angle created by the segment connecting the origin and then this point P, okay? So that is your theta. And then we can use this grid, okay, in order to plot, okay, your polar coordinates. Say for instance, we have P, okay, with coordinates 2, and then we have 15 degrees. Okay, so what is the meaning of this? Your r here is 2, and then we have theta, which is actually 15 degrees. Okay, say for instance, the grid here, okay, given is in degrees. Okay, so now if you have the center here, okay, and we have here r is equal to 2, you count 2 units, okay, away from this origin, okay. So this one would mean that you have of radius 2, okay. But we need to consider also theta, which is equal to 15 degrees, okay. So in this case, let's assume that this one is your 15 degrees, okay. This one can also be written in radian or in degrees, okay. So you consider those units, okay. So now this one corresponds to radius, which is equal to 2, and then I have here theta, okay, which is equal to 15 degrees, and your r here is equal to 2, okay. So meaning that the point that we're looking for is this particular point, okay, with coordinates 2, and then we have 15 degrees, okay. And then, in graphing polar coordinates, okay, or simply polar equations, this one can be done by substituting values of theta and determine the corresponding value of r, just like what we did in our example under graphing functions, okay, in rectangular coordinates. Remember when we are asked to plot additional points, you set values for x to obtain the value of y, okay? So this time, you can now substitute values of theta in order to determine the value of r, okay? So it is helpful to track, okay, both the degree and then the radian measure of the angles that you're going to use. And then choose whichever you prefer in identifying the value of r. Okay, and then consider choosing angle, okay, measurements in equal intervals. Okay, and then you're going to use special angles to simplify our computation. Okay, so I want you to consider the next video, okay, that will give you examples on how to plot, okay, um, polar equations in, of course, polar coordinates.
Lesson 6.5, Graphs of Polar Equations. Now, in the last lesson, we started introducing ourselves to the polar coordinate system as opposed to the rectangular coordinate system. Now, just like we can do in the rectangular coordinate system, I want to go ahead and start graphing equations, in this case, polar equations. Now, before we get started, you want to go ahead and hunt down some polar graph paper. If you're one of my students, you can find that posted on Parent Access. If you are not one of my students, I'm sure you can find it on the Google. So, graphs of polar equations. Now, remember that a polar function, instead of it being y as a function of x, we have r as a function of theta, where theta is your input value. That is an angle that you put into the equation, and r, which is your radius, is your output value. So we put in a theta, get out a radius, as opposed to putting in an x and getting out a y. Now, this is going to be the polar graph paper that I'm going to be using, and since I'm going to be using it all the way throughout, I'll go ahead and label each one of the spokes right here. That way we don't have to keep relabeling them over and over and over again. Now, remember, of course, we start with 0 on the polar axis. Now, it doesn't matter if you do this in radians or degrees. I am partial to radians, so I'm going to stick with radians. If you want to do this in degrees, you are more than welcome to do that, which means up here I'm going to have pi over 2. Now there are 1, 2, 3, 4, 5, 6 spokes here, the sixth one being pi over 2. That means halfway to pi over 2 I would have pi over 4. And then there are pi over 4 being the 1, 2 third spoke. If I divide pi over 4 by 3, that would make this one pi over 12. So each one of these little spokes is pi over 12, or in degrees, it would be 15 degrees apiece. So if this is pi over 12, this is 2 pi over 12, 2 over 12 being pi over 6, 3 pi over 12 being pi over 4, 4 over 12 would be pi over 3, and then 5 over 12, 6 over 12 being pi over 2. So all the way around, each one of these is going to be pi over 2, but of course, the more common ones that we're actually going to be using would be the unit circle values at pi over 6, pi over 4, pi over 3, and of course all the quadrantals. Alright, so let's get started with our first equation, r equals 2. R equals a number, usually a great place to start. Now, way back in Algebra 1, when you first started graphing, you learned to graph by just simply using a t-chart, where you would plug in an x value, figure out what the y value was, and then plot the points. Now, we're going to start polar graphs the same way, but hopefully, once we start noticing a pattern, we can get away from that plotting points technique, because although plotting points will always work, it tends to be tedious and make the problem much more cumbersome and difficult than it needed to be. So I'll start with my t-chart. Remember, it's theta and r, not x and y. Theta is your input, r is your output. And I'll go ahead and start making a list of possible thetas, and I'm always going to use my unit circle values starting at 0. And normally I'd go all the way to 2 pi, but on this one we're going to notice pretty quickly we don't need to go that far. So if I start at 0 and I think, here's my equation, r equals 2, let's plug in 0 everywhere I see a theta. Well, right off the bat, you should notice there is no theta. So if I plug in 0 nowhere and r equals 2, then r equals 2. And even if it's pi over 6, r equals 2. So in other words, at any angle, r is going to equal 2. It doesn't matter what the angle is, Because r equals 2. So if I start going over here to plot my points, it really doesn't matter what the angle is. The radius is 2. So I'll go ahead and start plotting points at the second circle pretty much anywhere I want to. And eventually you'll notice, hey, if r always equals 2, that's the definition of a circle. So if r equals 2, we simply have a circle with a radius of 2. Now, just for kicks, let's go ahead and change that up a bit. Instead of it being positive 2, let's say it's negative 2. Notice how it changes. So we can start off the same way, list out the angles, basically as far as you want, and once again, r equals negative 2, so it doesn't matter which angle I pick, the radius is always negative 2. Now remember, in the last section we learned about plotting polar coordinates, and we learned about what if the radius was negative. Well, if the angle is 0, remember the polar axis is an angle of 0. So if I start at the pole and go in the direction of 0 radians, but I go in the direction of a negative 2, that really means I'm going to back up 1, 2 right here. So I'm going to put my first point right here instead of in the positive direction. Now if I go up to pi over 6 and I try to plot the point at positive 2, I'm going to remember, nope, not at positive 2, I'm going to plot it at negative 2, which would be back here. And I could keep going in that direction all the way around. This was at pi over 6. Well, here's pi over 4, plotted at negative 2. Alright, here's pi over 3. Let's go back to negative 2. And notice, just like before, I can go ahead and plot it as many points as I want. It's always going to be negative 2. So here's my graph. Now notice, either way, whether it's positive 2 or negative 2, I get a radius of 2. The only difference is the starting point. When r equals positive 2, this was my starting point. When r equals negative 2, this was my starting point. But on both of them, I graph them in the same direction. Alright, because no matter what polar graph I'm drawing, it will always graph in a counterclockwise direction, because of course the angles, the positive direction for angles is counterclockwise. So just by making it negative, it doesn't reverse the direction, it just changes the starting point to the other side of the graph. So in general, I can say if I want to draw a circle in polar, I don't have to have any fancy x minus h squared plus y minus k squared like I do in rectangular equations. I can just say r equals a number. So r equals a, and a would simply be the radius. And of course, it graphs counterclockwise. If we start at a positive number, then I'll start here at 0 radians with a positive a. If I start with r equals a negative number, then still at 0 radians, but negative means I would start over here. So it would still graph counterclockwise, it would just start at a different point. But as far as direction goes, when we're doing polar, direction's not really important because it always graphs in the same direction. Either way, it's a circle. Now, I can do r equals a number. I should also be able to do theta equals a number, but we're going to find out pretty quickly we're not going to get a circle this time. So let's start off the same way. I'll do theta equals pi over 6. Well, since theta equals pi over 6, I can only pick one angle value for theta. It has to be pi over 6. It can't be anything other than pi over 6. What doesn't matter is the radius. I can pick any radius that I want as long as the angle is pi over 6. So if I start plotting points at pi over 6 radius of 1, pi over 6 radius of 2, pi over 6 radius of 0, negative 1, negative 2, what I'm going to start to realize pretty quickly is when it's theta equals a number, it's just going to be a line going through the pole. So whatever the angle is, whether it's pi over 6, pi over 3, negative pi over whatever, I'm going to have a line at that particular angle in the positive direction and the negative direction. Alright, let's start to get a little bit more challenging. Instead of it being just r or theta equals a number, let's go ahead and throw some trig in there. R equals 4 sine theta. So it's something new, so the first time I do it, I'll start with a t-chart. But once I've realized the pattern, I'll stop doing that t-chart completely. So I'll go ahead and list out my angles. Now this one I'm going to go ahead and list all the way out to 2 pi. And before I can start drawing the graph, we got to figure out the radius at each one of these theta values. So I'll go one by one using my knowledge of the unit circle to evaluate. So we'll start at 0. Sine of 0 is 0, so I get a radius of 0. Sine of pi over 6 is 1/2, so I get a radius of 2. Sine of pi over 4 is root 2 over 2. So I would get 4 times root 2 over 2, which is just 2 root 2. Pi over 3, I get root 3 over 2. So that would end up being 2 root 3 when I multiply it times 4. And then sine of pi over 2 is 1, so I just get 4. Now, my knowledge of the unit circle tells me I don't have to waste time continuing to calculate these. I know as I pass pi over 2, I'm just going to repeat the exact same values I did on the way up. I'm just going to repeat them on the way down in reverse order. So it would be 2 pi over 3, 2 root 2, 2 back to 0 when I get to pi. And then on the other end, it's going to be the same values, but now it's just going to be all negative. Back to 0. Alright, now I'm ready to start plotting. Now, when I start plotting, though, I need to remember these roots. I can't plot a root. I got to convert it to decimal. There's no need to grab a calculator on simple roots like this. Square root of 2, if I don't know what it is off the top of my head, even though I probably should by now since it's been used so often, square root of 2 I know is going to be a little bit more than the square root of 1. So I know that square root of 2 is going to be a little bit more than 1. I also know that the square root of 2 is a little less than the square root of 4. So I know it's the square root of 2 has to be somewhere between 1 and 2. Now, as far as where between 1 and 2 it is, it really doesn't matter because we're just plotting it on a coordinate axis, so it just has to be approximately correct. Now, I know root 2 is closer to root 1 than it is to root 4, so I know it's closer to 1 than it is to 2. So it's not going to be smack dab in the middle, it's going to be off to one side, and it just so happens the square root of 2 is 1.414, so I'll just go ahead and use 1.4. So if root 2 is 1.4, if I double it, I would get 2.8. So anytime I see 2 root 2, it's really going to be about 2.8. And then with root 3, I know it's going to be on the other side of the 1 to 2 split. So it's going to be a little bit more than 1.5. So we could say 1.6, although I happen to know it's really 1.7, so I'll use 1.7. So 1.7 times 2 is 3.4. And again, it doesn't have to be perfect. It just has to be somewhere between the approximate values. So let's go ahead and start sketching this out. We'll start at 0, 0, which is going to be right here. My next coordinate along the pi over 6 line is going to be at 2. Then once I get to the pi over 4 line, I'm going to go ahead and approximate about 2.8. So here's 2, here's 3, so 2.8 is going to be somewhere around here. Okay, about right there. Then my next line would be at pi over 3, and I'm going to approximate it to be about 3.4. So here's 3, here's 4, here's somewhere in the middle, about 3.4. Then when I get to pi over 2, I'm going to go ahead and plot my point all the way up at 4. Now I'll go ahead and decrease. Here's 2 pi over 3. We're going to go ahead and plot it at 2 root 3, which was the same height as I had over here, so it's got to match. At 3 pi over 4, I'll go ahead and plot it at 2 root 2. At 5 pi over 6, which is right here, I'll go ahead and plot it at 2. And then when I get to pi, I'll go right back to 0, which is going to be right here. Now, I've got some points here. I kind of start to see the shape, but let's go ahead and keep going just to make sure I see exactly what I think I see. Alright, here's the rest of the t-chart at 7 pi over 6, which is this angle right here. I'm going to plot it at -2, so I'm actually going to back it up to -2, and I find, well, hey, there's already a location, a point at that location. Let's see, so let's keep going. At 5 pi over 4, here's 5 pi over 4. I'm going to plot it at -2 root 2, which again is this point right here that I've already plotted. And I could continue to go through this chart, but I'm going to realize that each one of these negative values corresponds to one of these points that I've already graphed. So really, I didn't need to figure out the values all the way to 2 pi. From 0 to pi would have been sufficient to get my perfect circle. 4 sine theta is a perfect circle. So now that I know that 4 sine theta is a perfect circle, I can kind of generalize this type of format into saying that anytime it's r equals a sine theta, or for that matter a cosine theta, it's going to be a circle. If it's sine, it's going to be a circle on the y-axis. If it's cosine, it's going to be a circle on the x-axis. And it's going to be a distance of a along those axes. So instead of the a being the radius like it is on this one, a is actually going to be the diameter when it's of this format. So whether it's r equals a number or r equals a number sine, a number cosine, it's going to be a circle. So from this point forward, I don't have to waste my time plotting points. If I see one of these three formats, I can just go ahead and sketch the graph real quick. Speaking of which, let's go ahead and give that a try. So hopefully you found some graph paper, some polar graph paper. Here are 2 examples. Why don't you go ahead and give these a try on your own and then hit play when you're ready. Alright, let's look at the first one. R equals 3 cosine theta. Now, again, you don't want to waste time plotting points on this. If you recognize that this is just going to be a circle, we can just go ahead and draw the circle. So what we know about this circle is that the a value is 3, so that's going to be the diameter of the circle, and the fact that it says cosine means it's going to be the diameter along the x-axis. So instead of wasting time plotting points, I'll just go ahead and plot a point at 3 along the x-axis, 1, 2, 3, and then I'll go ahead and draw my circle. Now remember, it's not a circle following the polar graph paper, it's a circle from 3 back to the pole at 0, 0. So here is my circle, 3 cosine theta. I can do the same thing with negative 3 sine theta. Again, my diameter, in this case it's negative 3, that just means instead of going up 3, I'm going to go down 3. And I'm going to, again, do it in the y-axis. So here's my point right here. Draw my perfect circle. Easy peasy, no t-graph, moving on. Alright, here's something a little bit new, so we will go ahead and use that t-chart. It's got that 2 in there, which changes things up just enough for me to go ahead and do the t-chart to see what it actually looks like. Once I get the pattern, though, then I'll just go ahead and draw it from memory in the future. So here's my t-chart. We'll go ahead and list out our angles all the way to 2 pi, since I don't know exactly what's going to happen. And we'll go ahead and start plugging in to figure out what the radiuses are. So plug in 0. 0 times 2 is 0. Sine of 0 is 0. Plug in pi over 6. Pi over 6 times 2 is 2 pi over 6. Well, that's really pi over 3. Sine of pi over 3 is root 3 over 2. Root 3 over 2 times 4, 2 root 3. Plug in pi over 4. Pi over 4 times 2 is 2 pi over 4, which is really pi over 2. Sine of pi over 2 is 1, so we get 4. Plug in pi over 3, I get 2 pi over 3 again. Sine of 2 pi over 3 is going to be root 3 over 2, so I'm back to 2 root 3. Again, we get the same situation that we had happening last time. I went up to my peak, and now I'm just going to decrease back to 0. Alright, and then the way the sine pattern works, it starts at 0, goes up to its maximum, goes back to 0, but then it just repeats the same numbers in the negative. So it would be negative 2 root 3, negative 4, negative 2 root 3, 0. Then we'll go to positive. 2 root 3, 4, 2 root 3, 0, then to negative, 2 root 3, 4, 2 root 3, 0. Alright, so here's my values. Let's go ahead and sketch them out. Remember that 2 root 3 was really about 3.4 as we sketch it out. Starting with the first point at the pole, I get 0, 0. At pi over 6, it's going to be 2 root 3, which was about 3.4. At pi over 4, I've got a coordinate at 4. At pi over 3, I've got a coordinate back at 2 root 3. And then at pi over 2, I'm back to 0. So from 0 to pi over 2, I've got these 4, technically 5 points. Alright, let's keep going. At 2 pi over 3, I've got negative 2 root 3. So instead of plotting it up here, I'm going to plot it down here. And then the same thing with negative 4. And the same thing with the next one, negative 2 root 3. So these 3 values, remember, these are technically not 4th quadrant values. These are 2nd quadrant values that are being plotted in the negative. We can keep going. Now we're going to be on to the 3rd quadrant, 7 pi over 6, 5 pi over 4, and 4 pi over 3. These are going to be positive values, so I'll go ahead and plot them in the 3rd quadrant. Then when I get to the 4th quadrant, once again, negative values, so my 4th quadrant values are actually going to be plotted in the 2nd quadrant at negative 2 root 3, negative 4, negative 2 root 3. So when I connect the dots, notice the direction in which I draw it, again counterclockwise, has to match the order in which I plotted the points. So remember, I started right here at 0, 0, and then I went up to this point right here, then to this point, then to this point, and then back to 0. Now notice I curved it because it is a polar graph. It needs to be curved. It's not ever going to be just straight lines. So notice I got a little leaf looking thing right there. Now I didn't go to the 2nd quadrant next. The next set of points were these 3. So as I went through the graph, it's just going to be a nice smooth transition down into this quadrant. Connect the dots as best I can. Then we went into the 3rd quadrant, nice smooth transition. Notice I'm still drawing it counterclockwise. Beautiful, beautiful, beautiful. and then up here. And notice the shape I'm getting. Don't worry, I'll clean it up in just a second. And then I'm back to the beginning. So let's clean that up real quick. Boom. So what I have here are 4 leaves, and that's actually what we call them, 4 leaves or 4 petals. You can call it either or. And it looks like a little 4-leaf clover. Now, if you want to call this a 4-leaf clover graph, you are more than welcome to. In general, we call this a rose curve. Now, as these numbers change, we can get more or less petals. But in general, we call the classification a rose curve. So a rose curve is any equation, any polar equation that's of this basic format. Now we still have that same a value that we had before. That's going to be the radius. That's going to tell you how far out from the pole that the rose is going, or the leaf is going to go. And then the n value is going to determine the number of petals. The question is, how does that n value determine the number of petals? And to illustrate how the n value affects the number of petals, I'm going to go ahead and pull out my calculator and just go ahead and start putting in test values to see how this affects it. Now, because this is polar, I'm going to go to my mode, and I'm going to change my mode into polar mode. POL stands for polar. So when I go to the y equals screen, notice it's no longer y equals, it's no longer y and x equals, it's r equals. So on the last one, I believe it was 4 sine of 2 theta. So when I hit 2 theta, notice when I hit that variable button, it's going to pop up the theta because I'm now in polar mode. X is when I'm in function mode, T for parametric, theta for polar, and N for sequence mode. Alright, and then when I graph it, I see my 4-leaf clover. Alright, now I'm going to go ahead and zoom this in just a little bit. I'm going to change my window. Notice the window's going from 0 to 2 pi. My xmin and xmax, I'm going to go ahead and change that up a little bit just to make it a little closer. Remember, x, it's going to be longer in the x direction than it is in the y direction because of the rectangular screen. I'm going to make it -6 to 6 in the x direction and -4 to 4 in the y direction, just so we can see a little bit prettier close-up of the graph. Notice the path that it's sketching. It graphed it counterclockwise in the same direction that we plotted the points. So remember, this was sine of 2 theta. So look what would happen if I change it to 3 theta. I still get a rose curve, but this time it only has 3 petals. So I went from 2 theta to 3 theta, and it went from 4 petals to 3 petals. Let's keep changing that n value. Let's change it to 4. And see how many petals I get this time. Now notice, count them up, I have 8 petals. When the n value was 4, I have 8 petals. When the n value was 2, I had 4 petals. N value was 3, I had 3 petals. N value is 4, I have 8 petals. I wonder if you're starting to notice the pattern. Let's change it to 5. Alright, so at n equals 5, I have exactly 5 petals. So hopefully at this point you've started to notice the pattern. If I have an odd number for the n value, say, how about 9, let's jump all the way to 9, I can predict how many petals it's going to have, because if it's an odd number, I have exactly 9 petals. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whereas if it's an even number, let's go ahead and make it an 8. If I have an even number, I don't have 8 petals, I'm actually going to have 16 petals. So for odd numbers, we just keep that number for the number of petals, but for even numbers, we double it to get the number of petals. So we know that A represents the radius. If n is odd, we have n petals. If n is even, then we just double that number to get 2n petals. So on this one, since I have 4 petals, I know that the n value is 2. So we don't always have 4 petals. It depends on what the n value is to determine the number of petals. Now the question is, where do the petals begin? Well, notice for sine, I've got it up here. For cosine, I've got it right here. So with sine, the first petal is always going to be pi over 2n. Now the reason it's pi over 2n is we think pi over 2, that's where sine reaches its peak. At 90 degrees, that's where we reach our peak. So if I divide it by the number in front of theta, remember the period shift is the number in front of the theta, that's going to give me my new peak, just like it would give me my new period. So pi over 2 divided by n is just easier to say pi over 2n. So if the n value is 4, then I would be at pi over 8 for my first petal. If I was at n equals 3, I would be at pi over 6 for my first petal. For cosine, cosine reaches its peak not at pi over 2, but at 0. So really I could say that the first petal starts at 0 divided by n, but why say 0 over n? We can just say that the first petal always starts at the polar axis. I love having cosine because I don't really have to think about it too much. The first petal is always on the polar axis. For sine, we have to think about it a little bit more. Just take pi over 2 and divide by whatever number is in front of the theta. So here are 2 examples. Why don't you give these a try on your own? Hit play when you're ready. Alright, the first example, r equals 2 cosine of 3 theta. So we have 3 petals. Since the n value is odd, we don't have to double anything. That's just how many petals we have. The 2 represents our radius, and the fact that it's cosine tells me I'm on the x-axis. So I will start my first petal on the x-axis at x equals 2. Alright, so there's my first petal. Now I know I have 3 petals, so really all I need to do is take the circle and divide it evenly 3 times. So again, I can either do this in degrees or radians. I prefer radians, but if you want to do degrees, you can. Full circle is 2 pi radians, and if I need to divide that into 3 equal pieces, well, 2 pi divided by 3 is 2 pi over 3. That means starting at 0, every petal is going to be 2 pi over 3 away. So starting at 0, add 2 pi over 3. Well, here's 2 pi over 3. That means I'm going to have another petal at 2 pi over 3, 2. Alright, and then my next petal is going to be the next 2 pi over 3, which is 2 pi over 3 plus 2 pi over 3, or 4 pi over 3. So there's my next petal. I have 3 petals. Connect the dots. Rose curve. Alright, next one was 3 sine of 4 theta. 4 means an even number. I'm going to double it to say I have 8 petals. Each one is going to have a radius of 3. And since I am on it, since it's sine, I'm going to start my first petal at pi over 8. Remember, it was pi over 2 divided by 4, or you can say pi over 2n. Either way, you get pi over 8. Now, the problem with my graph paper is I don't really have a pi over 8, but I can find pi over 8 pretty quickly. Pi over 8 is simply half of pi over 4. Well, if this is pi over 4, half of pi over 4 would be right here in the middle of pi over 12 and pi over 6. So I'll go ahead and plot on the third circle. I'll go and call that pi over 8. Now, I know I have 8 petals, so I need to divide my circle evenly 8 ways. So if I have 2 pi as a full circle, then 2 pi divided by 8 would just be pi over 4. So every pi over 4, or every 45 degrees, I'm going to draw another petal. So if I'm at pi over 8 right here, if I add pi over 4 to that, that would get me right here. And then another pi over 4 would be right here, and another pi over 4 would be right here, and then right here, 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 and here. So there's all 8 of my points, all equally spaced around the circle. I now have my 8-petaled rose curve.